We discuss now a very important inequality called Cauchy-Schwarz inequality. So let's put it as a form of a theorem. The Cauchy-Schwarz inequality. So let's V be a vector space with the scalar product denoted as usual, and denote, so we denote for now norm of x, the square root of the scalar product of x with itself for every x in V, and we will eventually prove that this is a norm, but we don't know yet. So the first thing we will prove is that this inequality called Cauchy-Schwarz inequality, that the scalar product between x and y is always less than the norm of x times the norm of y for all x and y in V. And the interesting thing is that this inequality is an equality if and only if x and y are linearly independent. So we have that x scalar y is equal to x times y if and only if x and y are linearly dependent. Okay, and as a picture we should think it's this. Okay, so we have x, we have y, and what the scalar product is representing is the projection of one of the vector on the other. So in case we can represent this red vector is the vector that represents the scalar product between x and y. So it will be maximal when the two vectors are collinear. Otherwise, it's going to be less than the area of the parallelogram, which is this object here, of the the area formed by x and y. Okay, let's move and let's give a proof. So for the first part, so let's fix x and y in V, and let's consider the function g of lambda defined as the scalar product between with the notation that we used before is the norm of x plus lambda y squared. We can actually write this as using the linearity or the bilinearity of the scalar product. This is equal to lambda square norm square of y plus twice x y plus I forgot the lambda here plus norm of x squared. Okay, so this is a quadratic polynomial in lambda. So from the fact that scalar products are always greater than 0 if the vector is non-zero, we get that G of lambda is greater than 0 for all lambda. And so what we have that, so therefore this is in lambda is a parabola, it's always greater than 0. So if a parabola is always greater than 0, then necessarily has at most one solution equal to 0, so which means that the determinant is negative or non-positive. So the fact that G is a quadratic polynomial that is always non-negative implies that G equals 0 has at most one solution, which implies that the discriminant of the quadratic equation should be negative. And what is delta? So delta by the formula b squared minus 4ac, where this is a, b, b is this, and c is this. Okay, so what is this? This is equal to 4xy squared minus 4 norm of x squared norm of y squared. Okay, so this thing is non-negative, so let's write it again. So this is xy squared less or equal than norm of x squared norm of y squared. Now let's take square root and recall that then a scalar product of elements with itself is always positive. So what we get, so take square root and recall that norm of x, norm of y are non-negative. So what we get is that actually the absolute value of xy is less or equal than norm of x times norm of y. It might look stronger than the Cauchy inequality, but this is, of course, once you bound without the norm, without the absolute value, just changing x to minus x will give you the bound for the absolute value of the scalar product. So the Cauchy-Schwarz inequality is proved. Now what happens if we have equality? Equality means that this means that this discriminant is equal to 0. Now either the function is constant or it admits one solution. So second part, so if now xy is equal to norm of x times norm of y, this implies that the determinant is equal to 0. Now, so if y is equal to 0, then there is nothing to prove that this linearly independent, if it is linearly dependent on x. So if y is different than 0, then G is a quadratic polynomial, non-constant. So therefore we have that there exists a solution G such that there exists some lambda such that G lambda is equal to 0, which means that there exists some lambda for which the definition was x norm of x plus lambda y is equal to 0, but we know that the scalar product with an element on itself is always positive unless the vector is 0. But then we get that x plus lambda y is equal to 0. So we again have that x is linearly dependent on y. This is the end of the proof of Cauchy-Schwarz inequality. One of the first consequences of a Cauchy-Schwarz inequality is the fact that the norm induced by a scalar product is indeed a norm. So corollary. So if you have a scalar product on V, then the norm, the function defined as square root of x, this is a norm. Let's prove it. So let's check that scalars go outside. So this is square root of lambda x. So this is equal, because it's a scalar product, goes lambda square x. So take each one goes out. And this is equal to absolute value of x, norm of x. So this was the first thing to check. The second thing to check is the triangle inequality. So x plus y, so this is square root of x plus y. And now this is, let's use, then it's a bilinear plus 2xy is bilinear. Okay, and now we use Cauchy-Schwarz. This Cauchy-Schwarz tells us that we can bound, see, all these are positive. Now this thing, it's smaller than each of the norm, right? So this is x squared plus 2 norm of x times norm of y plus norm of y squared. Okay. Now this is a square. This is exactly x norm of x plus norm of y all squared. So these are positive numbers, so this is equal to norm of x plus norm of y. Okay, we have triangle inequality. And the last thing, we have that the norm of x is greater than 0, of course, if and only if the scalar product is greater than 0, and that's true. So the only element with 0 norm is the 0 vector. Okay. Now, so which means that every vector space with a scalar product has an induced norm and therefore has an induced distance, which therefore has an induced topology. Let's write this as an important remark. So every vector space with a scalar product, so with a choice of scalar product, has as this canonical choice of norm and of distance, and therefore and a canonical topology. Okay, but one should pay attention that not all norms come from a scalar product. And actually, one can detect from the norm if this norm is coming from a scalar product, and it's actually going to be unique if it exists. So this is a fact that we might discuss at some point. A norm, let's call it as usual, comes from a scalar product. This terminology means there exists a scalar product whose norm is associated norm is the norm we have if and only if the parallelogram law holds. The law is the following: twice the norm square plus 2i the norm of y square is equal to the x plus y square plus x minus y square. Picture means that, so if this is x, this is y, then this is x plus y, and this is x minus y. So we have these rules for their length. And in this case, so if this is true, if this parallel law is holds, then we have that the scalar product is equal to 1/4 of norm of x plus y square minus x minus y square. Of course, one can really like write down this as a scalar product and check that this inequality holds. So which means that if there exists a scalar product, then it's uniquely determined by the norm. So let's write it as a sentence. So each norm comes from at most, so it could be none, but if there exists one, there is exactly one. It's one scalar product. Okay. So we shall work with norm vector spaces or vector spaces equipped with a scalar product. But there will be an assumption that is going to be very important for the theory, is that the metric that they define is a complete metric. So let's define what is the completion. That's one. So a normed vector space let's call it V, norm V, is complete if it is complete as a metric space. Now I remind what it means. Space, which means if every Cauchy sequence converges, if every sequence, let's call it xn V, such that for all epsilon greater than 0, there exists some n, such that for all n and m greater than n, one has xn minus xm less than epsilon. These are called Cauchy sequences. So if every Cauchy sequence converges in V, and this of course means that there exists a point in V, there exists a x in V such that the norm between x and xn goes to 0 as n goes to infinity. Okay, now that we know what is a complete metric space, now we say that a complete norm vector space is called Banach space. And a Banach space for which the norm comes from a scalar product is called Hilbert space. In other words, a Hilbert space is a vector space equipped with a scalar product for which the associated distance is complete. Cauchy sequences converge. We will mostly study infinite dimensional Banach spaces or Hilbert spaces. And it's going to be very important to distinguish between different norms and different topology that one obtains in infinite dimensions. That's why, and these problems don't appear in when the dimension is finite. So that's why I want to briefly tell you that our point of view for finite dimensional settings is very easy. So let V be a vector space of finite dimension. So V as a linear space, as a vector space, is linearly isomorphic to Rn. We have the choice of a basis where n is exactly the dimension, some n in n. But of course, there are several norms on Rn. So let's take two norms on Rn. So what is true is the following. One, so there exists a constant such that the norms are equivalent up to this multiplicative constant. In other words, let me say that the identity map from Rn with the first norm to Rn with the second norm is by Lipschitz. There's a by Lipschitz map. 3, so which implies that we can take the usual norm, the Euclidean norm, for example, and any other norm, and what you obtain is a by Lipschitz equivalence, and therefore the topology is the same. So V, with a choice of a norm, has the same topology of the standard Rn, which means in particular there's only one topological vector space of dimension n. Okay, and in particular it's complete. So all finite dimensional normed spaces are Banach spaces. And in dimension 1 and in dimension n, it has the topology of Rn. It is by Lipschitz to the Euclidean Rn.